You can go ahead.
Okay. Yep. Well, so first of all, welcome everybody. So today, since we are getting close to Christmas, and I think I gave already this talk 10 years ago, it had changed a lot now. So I thought it was good to review where we are standing in the understanding of gravity. Actually, the Universal General Relativity is typically says 25th of November when he published the questions, but actually the questions appeared in the December 3rd, so it was like a couple of days ago. So I will try to do something more from a historical perspective, but and also conceptual, trying to minimize the questions and everything like this. So, and I have divided all the history in a prehistory, the genesis, where I will probably spend most of the time, how this thing emerged. Then there was a time of glaciation where nothing happened, in the last century. And then there was a golden age when technology was getting better and also theory was getting better, and people changed completely the perspective. And now I will finish, well, this part of historical, where are we going and what is the contemporary perspective. Okay, so let's start from the prehistory. So the prehistory is almost the history of science, right? So when Galileo already established, I think he understood pretty well the idea of the principle of relativity, which basically nothing but that the laws of physics have to be the same for any observer, but not for all of them, only the ones that were inertia, right? So, which is always this kind of thing that is like a loophole where what is inertia, what is real forces, and you go around. But anyway, we can discuss about this. But especially, there is this legend. I think this never happened, but okay, he did other kinds of experiments where he understood by throwing things and studying the motion of things that the way you can imagine that there is no atmosphere, the way bodies fall doesn't depend on their mass, it doesn't depend on the composition, and therefore there is actually he was even able to manage to understand that the acceleration and the gravity goes like with the time square, and where g here is the acceleration of the Earth, or you can call it the Earth's surface gravity. And okay, I was going to say something more, but I don't know. I didn't put it. Okay, this is the universality of free fall. This is what very importantly Galileo understood really very well. Then it came Newton, which was kind of the synthesis of everything everybody did at the time, but he managed to put it under his name. And basically, he had, from one hand, we had the laws of motion. Things already Galileo knew, like the first law, which defines inertial friction. Well, it means that you are in a motion in a straight line or at rest, you will continue like this. The second law is that the force equals mass times acceleration, which is only valid in the inertial frame. So otherwise, you need to add inertial forces, centrifugal forces, whatever. Gives you acceleration. And then the third law, that is for every action there is an equal or an opposite reaction. Okay, we know these laws from high school, I guess, right? But then one thing that Newton realized, and now seems obvious, but at the time was not obvious at all, is that the gravitational phenomena at the Earth and the planets going around the solar system are the same phenomena. At that time, it were two completely different things, right? There was people inventing like spheres where the planets were attached and all kinds of things, right? So he realized that it was the same phenomenon, and that was gravitation. He established the universal law of gravitation, which actually explains the whole dynamics of the solar system. Basically, the idea is that the planets are falling all the time, but they are falling towards the sun. But since the sun is much smaller than the size of the orbit, they never find the surface, so they keep falling. So everything is falling, right? That's gravity is falling towards somewhere. That's what what is gravity in reality. Anyway, but let's have a closer look to the formula that we learned in high school, right? You have one object, one that has one mass 1, and object 2 has mass 2. They attract each other, and this is the formula. But I have put here a G. So the idea here is that the property of the bodies that make them attract each other gravitationally doesn't need to be the same as the mass that appears in Newton's second law, right? which is that we call typically this inertial mass, and this is the gravitational mass. We are very used that this is are always equal, and we don't worry anymore. But for Newton knew already that it didn't need to be like this, right? Another thing that this formula was very uncomfortable, especially for philosophers at that time, is that this is an action at a distance, right? Without not mediating anything. That was something people didn't like too much. But okay, it worked, so why not, right? I mean, okay, so then when you have Newton's law of motion, right, it gives you the mass time acceleration is the force. If the force is the gravitational force, you plug it in there. Then you have here this formula for the acceleration of the object 2, which has two parts. One is the gravitational field of the other object, which doesn't depend on the object 2, depends only on the object 1. And then, but here you have a factor that depends on the mass of the object 2, right? And somehow the composition. So, but people knew that the gravity, I mean that the free fall is universal. Therefore, so they established that this inertial mass and the gravitational mass must be the same thing. This is what people call now equivalence principle or weak equivalence principle, but that depends how you like. Okay, but I mean, this is something that people was already aware at this time. Okay, so then nothing happened. I mean, people lived happily with Newton's law until almost the last century. I mean, no worries, everything was working very well, right? But then there started to be experiments and even ideas that were already trying to, get in conflict or with the ideas of Newton. So what typically we call the genesis is all the set of experiments and observations that led to motivated the theory also, and all the theoretical developments that happened around the 1915, which is when general relativity is finally formulated. So regarding the experiments, there were three main experiments. One is the Elbos experiment. This is precisely to test this equivalence principle, the equality of gravitational and inertial mass. The Michelson-Morley experiment, I will tell you a little more, but you know probably what it is about. Well, actually, I say 3 is 4. The advance of the perihelion of Mercury, which, okay, it was there, but people actually really didn't worry too much. You will see why. And then the deviation of light when passing near massive bodies. Well, again, this was a bit later, so we will see. Then the theoretical developments that happened at the time is, that there was this 1905 was this fantastic year for Einstein, where he published almost all his great works. So and then all the development that Einstein did between this year to 1915, in principle, the principle of equivalence, what is unrestricted. I mean, all these things I'm going to tell you what happened a little bit and why it happened. So the Elbos experiment, I mean, there were already other experiments, but this was the first experiment in 19th century that really was paved the way through the modern experiments in gravity. I mean, he used distortion pendulum, which is actually until very recently is the type of experiments that we are using till today. Right now, quantum sensors and quantum experiments are getting into are already catching up, but most of the results you will see are based on torsion pendulums. And the idea is that there are here two forces: the force of gravity that goes to the center of the Earth, and then you have the centrifugal force. So basically, the experiment is designed that if the gravitational mass doesn't equal the inertial mass, then there is a torque because there is a net force. And then you have here a mirror with light. You can very precisely measure how this is twisting. And essentially, what you measure is what is called the Elbos ratio, that basically, in the end, gives you the difference of ratio between gravitational and inertial mass for the two objects. And already at the time of Elbos and his school, they were able to constrain it to 1 part in 10 to the 8, which very, very, very good. I mean, there were other people, as I said before, they did the experiment, but there was pushing this several orders of magnitude. So that was a big thing. The other thing was the Michelson-Morley experiment. I mean, basically, as I will tell you, there was a mess between the Maxwell theory of electromagnetism and classical mechanics, because it turned out that Maxwell theory was not invariant under changes of, translations, for instance, in space, right? I mean, in principle, Galileo told us that the laws of physics should be the same in every inertial reference. So the Maxwell laws were not invariant. So then people started inventing things like the ether, and then basically this experiment, by using interferometry, was telling you, it's like, okay, if it is the ether, there will be a preferential direction, and then we should see some interference here because we are moving we are moving inside this ether, right? So there will surely not all the directions are equivalent, and therefore we should see some interference. But okay, they didn't see anything. They didn't see anything to a very high precision. So okay, so then that's the motivation. What I was saying for doing special relativity, and the experimental motivation was that okay, there was no room for the ether theories or anything similar. So then Einstein came on this postulate, but probably contrary to general relativity, there were already people that were very close. There was Lorentz, there was Poincaré, there were other people that were really, really close to it, but they didn't probably dare to make the breakthrough, to promote things to the level of postulates, which is what Einstein did. So basically, the first one actually is the same as in classical mechanics. Is the principle of relativity of Galileo, only thing that is in a different context now, but it's certainly the same. The important thing is that the speed of light in vacuum has to be the same for all the inertial observers, which is a bit weird, right? I mean, because you move and with respect to somebody else that is throwing a laser like me now, and we still see the same velocity, right? That was was something that break the minds of people at the time. And this is what motivated the change from the transformation laws of Galileo to the ones of Lorentz, the Lorentz transformation that you probably, those of you that have done special relativity, have seen. Okay, then we have a special relativity. It had these profound consequences, like the idea of simultaneity now is relative, length contractions, time dilation, and something that it was very important, and typically people write E equals mc squared. But the interesting thing, which actually Einstein thought about, is the fact that the inertial mass depends on the energetic content of a body, right? So basically, and in this simple way. So basically, you divide by c squared, and that gives you the inertial mass. And actually, Einstein already was thinking that inertial mass should be the source of gravitational field. That's why this is very important. Okay. Came with this idea of measuring intervals, but now in space-time. We have a term with time that is now negative, right? This is what the people call the Minkowski metric. Apparently, Poincaré already knew, but Minkowski didn't cite him. Typical, right? But then the next year, apparently Minkowski died. So okay, a mess. You talk to French people, they will tell you this is the Poincaré Minkowski metric or whatever. Right? Anyway, but the important thing here is that now you have the light cones. Basically, the light cones are when you are an observer here with this space-time coordinates, and you throw light rays, you form a light cone, right? So, and this thing here tells you whether you are in causal contact or not with another space-time event, right? So if you are outside the light cone, then this is what is called a space-like connected events. Then you are not causally connected, so you cannot. So you are here, you will never communicate with this event. There is you are in the light cone, you are light basically. You cannot be light, but we are not light, so you cannot be in the light cone. So probably you are better in the inside, where it means that this observer will influence or will send signals to everybody that is inside the light cone. This is the nice idea of this thing. Okay. This is another thing that has a lot of importance, but it was not appreciated at the time, which is the advance of Mercury spirit here. It was realized by this astronomer who actually, I don't know if it was him or other people, but they did a lot of calculations, I mean, for this thing, right? So actually, Einstein knew from very early times about this. So the total advance of perihelion is like 500, 600 arc seconds per century. Sorry, per century, once only. Most of it can be explained by Newtonian gravity, actually. Right? So most of it is precisely due to the precession of the system of reference in which we are. And the rest of the Newtonian part is explained by the influence of planets. In particular, this is the breakdown, how many arcs per century each planet contributes. So you see Venus, because it's very close to Mercury, is one of the more contributors, Jupiter, and then is Uranus and us. We are contributing. So in total, you have these 500 arc seconds. So just to tell you something, there is also the possibility that the sun is not completely spherical; it's a bit oblate, and that will also contribute. But you see, very small. Although this created a huge controversy in the 60s, a huge controversy. Well, because actually people didn't measure it properly. But anyway, so then there are 43 arc seconds that are unexplained, right? So yeah, some people like Lorentz and Poincaré tried before Einstein to explain this, but they didn't get the real value. Actually, they were like a factor out of it, but they didn't even realize they were a factor out of the real value. So, but in reality, people didn't get very much. So, well, okay. So, I mean, probably somebody measured something wrong, right? I mean, this is what probably happened. Okay, anyway. So actually, but just this is the biggest one from a planet. You see, the next ones that are the ones close to the sun, this is, you see, it's getting very, very, very small. So it was not even, we were not even able to measure it. So Mercury was the one. Okay, general relativity, theoretical motivation. Similar to special relativity. Now, Einstein fixed the problem with electromagnetism, and then he created a problem with Newtonian gravity, because now Newtonian gravity is not the laws of Newtonian gravity are not invariant. And you do a Lorentz transformation, you go to another inertial frame. It's not the same law. It changes. So this is a problem, right? I mean, but okay, people didn't care too much, and in the end, gravity was very weak. So, what? So what? And then there was the experimental motivation. Basically the advance of perihelion, but people didn't care either, right? So the only people that cared was Einstein, probably, and this is why he was the only one working on this, right? I mean, so while other people was doing other things. Anyway, just to tell you about this, is like the idea is that you see gravity now as a field theory, like, I mean, the Poisson equation, right? So density creates tensor potential through the Poisson equation. Actually, this is already problematic because there is no time evolution. So the propagation of gravity in Newton's theory is infinite, it's instantaneous, right? This is another philosophical problem that was floating around at that time. So yes, this thing is not invariant in the Lorentz transformation, so there is a problem, a theoretical problem. Okay, so then while Einstein was still in Bern, he was in Bern when he did all these breakthroughs, right? He was in this patent office. Apparently, he worked like from 8 to 3, I don't know, something like this, and then he was free, and then he was working on physics. This is what he liked to do. And then one day, apparently, he was reading a newspaper of Bern, where some guy that was fixing a roof fell down with all his, tools, right? And then, probably most of the people in Bern didn't thought about this, right? I mean, but then I he realized that, okay, fine, this guy is falling down, and then he was imagining the hammer falling with him, all these kind of things. Oh, it's like, and he realized that the guy saw the hammer, next to him, right? Like if nothing was happening. So you're like, oh, he has canceled gravity, right? So, and then this idea of that when you throw yourself in free fall, you cancel gravity, is what he calls the happiest thought of his life, right? And actually, in this year, this strange journal of Relativität and Electronics asked Einstein to do a review of special relativity. So he decided to do a kind of a section on this idea, right? So it was called On the Relativity Principle and the Conclusions Drawn from It. And basically, well, he didn't talk about the guy falling down from the roof. Probably was not very polite either. So he presented this idea, this well-known idea, right? That if you are, that these two situations are equivalent. Either you are far away in space, far away from all the planets, and then you are accelerating, your rocket is accelerating with this acceleration minus g. This is equivalent to be on the surface of the Earth, feeling the gravity we feel at the surface of the Earth. Right? Basically, you do whatever is an experiment here is an experiment locally. You make this very big and you start thinking that move around, then it's not true anymore. But locally, this is how it is, right? So then he explained this idea, okay, so at some point he worked more on this, and then he did this paper where it was about the influence of gravitation on the propagation of light. This is already in 1911, right? And all this paper is basically, applying the idea of the equivalence principle. It's really amazing, but it's most of what he was doing, applying the idea of the equivalence principle. So then he realized that the rate at which time passes depends on the position within the gravitational field. This is what we call time dilation due to gravitational field, and this leads to a gravitational redshift. So the idea is, again, you have an accelerating frame that is equivalent to a gravitational frame. So he said, okay, I can do the calculations in the accelerated frame, and then, boom, translate the result to the gravitational field. And this is what he did. He imagined one clock near the surface, another clock to a certain height, and then he realized that the relation, how the ticks go here and here, is that this one goes slower. You see here is 10 and here is 12, right? So basically, and this is due to the gravitational field, which actually is negative. This is why this is smaller than this one, right? And you can do like apply like what will be the Doppler, but with the equivalence principle, you convert it into this gravitational redshift. And again, what happens is the opposite, is that the frequency, well, the frequency here is not the frequency here is bigger. Yeah, should be the opposite. I don't know if the sign is correct. Let me see. Yeah, I think I probably made a mistake. It should be the other way around. Well, this is the gravitational redshift. The thing he realized, again, equivalence principle, is that you are in a accelerated frame and you have a hole in the spacecraft, right, in the rocket. Then, because it is accelerating when the light enters and you are accelerating, not uniform motion, accelerating, then you see the light will go. You will see that like the light goes down, and then okay, he said, okay, I can compute this in a accelerated frame, and then I do equivalence principle. I translate to gravitational field, and this is what he did. And then, well, what he found is that effectively it's like if the speed of light depends on the gravitational field, right? And then he computed for the case of the sun. Now, when light passes very close to the surface of the sun and gets deflected, he got this simple formula, which tells you that this is 0.83 seconds of lensing. But actually, for this, he was using, for the part of the gravitational field, he was using the Newton's formula, right? So this is only half of the relativistic value that he didn't know at that time. Okay? Actually, he convinced people, in particular Erwin Freundlich, that why don't you go and do the measurement with one of these absolute eclipses, right? Okay, actually they mounted a whole expedition. The problem is that the eclipse was in August 21st in 1914, but just before the Germany declared war, I mean, flash World War to Russia. So Russia didn't. Actually, we were going to go to Crimea. Apparently, it was in Crimea where you can see this. And now again, Russia, as you can see, as you know. And then, okay, Russia said, no, nobody is going to pass by. Actually, they even took people. So basically, it was aborted. Actually, it was lucky for Einstein because the value was wrong, right? So the value he predicted is this, which is wrong. Okay. Anyway. So then he moved to Prague because they offered him a professorship there. And he started thinking, okay, now, I mean, he abused, not abused, but he had been using the equivalence principle all the time. Has been very fruitful, right? I mean, many results. And he was, trying to see whether he can get other tools to progress, right? So then he was thinking about this idea of Minkowski of this interval, this interval in space-time. Then you can put it in like infinitesimal intervals. This is just a mathematical thing. But then he realized that all these results he got, he could recover them by putting that the speed of light depends on the position, and depends on the position the way he found using his reasoning, right? Okay. On the other hand, he knew that the gravitational field should be a combination of pure gravity and inertia, right? Like in the tendency of avoiding getting in motion, right? But he didn't know how to do it. I mean, he was here, but he had to. He had the idea that he was thinking about, because Einstein knew a lot of electromagnetism, is the idea that electromagnetism, actually in Newtonian gravity, you separate two elements that are very important. One is the field equations. One is that how matter tells the field how to change, how matter determines the gravitational field, or in the case of electromagnetism, the electromagnetic field, or whatever, in any theory. And the other thing is that now, once you have the field, how the field tells the matter to move. Like in the case of Newtonian gravity, the Poisson equation is how matter tells the gravitational field what is the value it has to take, and simply the gradient of the potential gives you the acceleration of anything that is moving around. So he knew that these two things could be separated. So he started thinking in those terms to see whether he could do something in the case of gravity in the same line of thought. Okay. Actually, he realized that for the case of gravity nearby the Earth's surface, this term here is actually linear, right? Because it's that G is almost constant nearby. So okay, so he realized that then this satisfies a kind of a Laplace equation. Oh, wow, this starts looking familiar, right? And then he said, okay, surely there must be something type of Poisson equation where you have here the density, whatever. This is the speed of light, by the way. The speed of light how depends on the position. Then he focused on, basically he was thinking about the stationary fields, like our field. I mean, our feeling as an approximation. I mean, there are many fluctuations, and people in gravitational waves, we know fluctuations are killing us all the time. But for this, we can assume that we are in a kind of stationary gravitational field. So he was working on these ideas. So he realized that if the source if the source of gravitational field is energy, energy, then energy in any theory is typically derivative squared, right? You see, this is how it is. So he said, okay, I'm going to put a term like this, and then he postulated this equation of motion. I said, okay, but then you see here, this is the first time he realizes that the theory has to be nonlinear. So if you want, if inertia has to be the source of the gravitational field, then there is no way you must have nonlinear terms. So it has to be a nonlinear theory. So he already realized in a very, well, natively maybe is what. Okay, more things. Then he convinced himself, yeah, but okay, this thing here has many, it's like a matrix, right? And applied to this, the vectors of displacement, right? Why only have to change one object if in general I have like 10, right? So he convinced himself that it couldn't be, that the final theory couldn't be that just changing one object inside there. That was a bit not the right thing to do. And then another thing that he liked a lot, it was another thought experiment. Although this I think was started by Ehrenfest a little bit before. And this is the typical, and probably people have seen this, is the idea of a disk in at rest and a disk that is rotating, like the merry runabout, right? So you have a reference frame, which is when you are on top of the disk. Another one is where you are outside and you see how the thing is rotating. But this rotation is acceleration, right? So he said, okay, equivalence principle again. There must be a gravitational field here, right? I mean, you see, in the end, it's not the lines of thought are not really super complicated. I mean, well, but I mean, they always use the equivalence principle. So he said, okay, if I am in top of the disk, I have to see the same thing as Minkowski told us. I can put it in a spherical cylindrical coordinates, which is much simpler because there is a symmetry around the axis of the disk. Okay, until here, I think everybody at that time was following then. And then the other one, the only difference is that the angle now is with respect to the angle outside is that you have omega, which is the angular velocity t. Okay, so he made a change, and then okay, you start having a strange thing, right? Okay, a strange metric where you have now more terms that have dependence on the position, blah, 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 blah. Actually, one thing that he realized is that when for the observer outside, that is then the spatial metric is, well, he didn't realize about this. And he did it in a very different, because he didn't know too much of this geometry, but now we can take advantage of what we know. So basically what happens is that the geometry is now curved. And then if you compute the circumference for somebody that is outside, it gives you that the circumference divided by 2 pi r, which is the value in Euclidean geometry, is in general, if the angular velocity is not 0, is in general bigger than 1. And he was like, wow, what's going on here, right? I mean, so this means that the geometry of a space is in the presence of gravity has to be curved. So you see, he convinced himself that it has to be nonlinear, and he convinced himself by doing these little tricks and thoughts that it has to be there has to be curvature. So this is how I mean, you see he's like advancing slowly, but okay. So then he said, okay, I'm going for it. I have to learn this mathematical theory of Gauss and Riemann. By the way, nobody understood Riemann at the time of Einstein. So okay, I don't know. So he was a bit worried. Okay, and then we were competitors like Ricci and Levi Civita that did a very good job in translating for the humans the work of Riemann. And people, so he was okay. Let's see what happens, right? So then, okay, yes. But before leaving Prague, he solved the part. We said that there is the part of the field equation and the part of the motion. He solved the part of the motion. He said, okay, I don't know what are the field equations, but I know that a test body, a body that doesn't gravitate, or we can neglect the gravitation, it has to follow geodesic of this metric, which is okay. It's the minimum path. It's just generalizing the idea of the minimum axiom, right? So okay. So then he returned to Zurich. Actually, it was let me see. Okay, yeah, it was going to. Okay, he returned to Zurich. I will tell you why he returned to Zurich. But then he had a long list of ingredients he wanted for his theory. You see, generalized relativity principle, geodesic, that you have this is something that he was insisting, and this is wrong. I mean, this equation I showed you before for the speed of light, this is a question doesn't make any sense. Well, now that we know, gravitational energy as source of gravity, integral limit, Mach's principle is the idea of that inertia is determined by the far distant objects in the universe. And then he knew from special relativity that the right description of matter is the stress in the tensor, so it should appear in some way. But he wanted all of this inside, right? I mean, which is, I think, something that stopped him. So in Zurich, actually, he went back to Zurich because his friend and classmate, his father, I think his father already managed to get him the work in the job in Bern. He got a job in Zurich as well, right? I mean, so he went back there and he started working with him because Marcel Brommer was a mathematician, and he said, "Okay, you have to help me, right? Because I don't know how we are going to do this, right? I mean." Actually, people found a notebook that he started in Zurich. Actually, it's called the Zurich notebook, because it contains all the calculations he was trying to do all these years to get to the final solution. Right. So one thing that just a comment is that now it seems, in difference geometry you have equations are invariant under any coordinate change. Now it looks very clear. At that time, nobody knew what it was. So actually, he was not even imposing this. Actually, at some point, he even convinced himself by a grown argument that he made himself that you should not consider this. Okay. Anyway, so okay. So they tried to make as hard as possible to make all these ingredients. I'm not going to enter into this. There are actually now we have people that have been doing research in the last years. There is a book for historians of science, more than 2,000 pages that you can read if you want, and they will tell you all the struggles that come from this. But So they wrote a paper that was called the Enwood paper, which basically means like a draft of the theory. This is so. I mean, they didn't dare to say this is the theory because they were not completely convinced. You see, it was published. I think it was in 1913, and there was a part by it was the physics by Albert Einstein, and then the mathematics by Marcel Grossman. Basically, it was they divided said like, okay, I am the guy, and you are the the housekeeper. Okay, anyway, okay, so they presented here the theory. They did the best they could, satisfying Einstein requirements, but they start realizing soon that there were problems started accumulating. And it was not general covariant, didn't provide the right perihelion advance, which already he competed with another friend of the school, Michael Besson, in 1913. By the way, Einstein, when he was at ETH in Zurich, he didn't go to the classes of mathematics. But Marcel Grossman did, and Marcel Grossman apparently was taking very good notes, which Einstein then read before the exams, and this is how he passed the exams on mathematics. So, it was this relation. Okay, anyway, then he realized that the rotating metric, problems started accumulating as they were checking things. So then he got a position in Berlin. Actually, Planck convinced him to go there as a full professor, a big guy, But Planck wanted him to work in quantum theory, and he didn't do anything about quantum theory. He just worked on gravity, which Planck was not very happy about. Another thing is that, we are in the summer of 1915, we are getting closer. He was invited to Göttingen by David Hilbert, the big mathematician of the times, right? I mean, he was invited to give to tell, okay, explain me this theory you published with this other guy, this friend of you, and what is this about? Because in Göttingen, they were very experts in variational principles, and Einstein was not, and so, okay, he was interested. The problem is that Hilbert got really very interested to the point that he wanted to try himself to find the right equations, right? So Einstein said, okay, wow, this is getting serious now. I have to reconsider all my ideas. So basically, he started not from scratch, but he started looking at everything now, like checking everything whether it was new or not. And then in November that year, he was invited to, well, I know he was invited or he invited himself, I don't know. Went to the Prussian Academy of Sciences, where, every lecture he gave could be published as a proceedings or paper. I don't think it was a paper. It was something between papers or proceedings that were almost published automatically. But then Einstein went 4 days and he published 4. Basically, every day was, correcting the previous day because, no, forget about what I said yesterday. Now it's the real thing. Anyway, in the end, he managed, and in the last lecture, he published the field equation. Right? So if all the equations that contain gravity is an approximation, blah blah blah, and then he sent his son that he had just completed the most splendid work of my life. And then here there was general covariance. It was a variational principle. I don't know if he put it in the paper. The right prediction for the advance the perihelion of Mercury, the correct Newtonian limit, the correct gravitational lensing, and basically, this is how the equations we say. Now we say, this is the field equations, the stress energy tensor sources gravity. This is an Einstein tensor. It's a complicated tensor in the metric, derivatives, and nonlinear terms. Basically, it's a derivative square, as he already thought. And then, this is an identity. But this is a local conservation. So basically, the theory unifies the equation of motion and the field equation. This is another great thing of this. And now you have general covariance, everything is wonderful. And then, well, this is a summation of indices, which also he invented. And the gossip is that, okay, so there have been a lot of controversy about this because Hilbert published a paper saying, okay, no, this is how you do things. I have here a Lagrangian, you do the variational principle, and you get the field equation. But he didn't write the field equations. Actually, he believed Einstein word by word. He even says in the paper that they cannot be covariant. They cannot be covariant. They have to be something else, right? So actually, we know now that Hilbert, he was changing the proofs to include the results of Einstein, right? So Einstein was really, really upset with him. But in the end, apparently, what happened is that, okay, so they said, okay, you and me, we are geniuses, so we have to understand each other, right? And then apparently Hilbert managed that Einstein got a prize, but apart from mathematician, which is wow, right? But apparently they say something like, okay, anybody in Göttingen knows more mathematics than Einstein. Okay, but the guy found the questions. Okay, well, right? This is what a little bit happened, but in the end, they understand each other. Okay, anyway. Then, you know, the history, I am going very slow. Okay. No, then later we know that especially for a solution for the stereo of a spherical object, that later, until 1958, there was not a good understanding that this was the idea of black holes. This is when black holes, actually black holes, the name already comes from the 60s. So it's very late. Actually, many people even today doesn't understand what a black hole is, but okay, anyway. Then in 1916 and 1918 was the years he studied gravitational waves. This is the first one, and the second one, he studied the properties, the energy of gravitational waves, the fluxes. There was a factor of 2 missing that Landau found later. Okay, what else? Okay, and then we arrived to 1918, and this is where another expedition goes to try to measure the deflection of light, another total eclipse. And this time is led by the famous astronomer Arthur Eddington, the big guy of the times in astronomy. And yeah, I mean, they got the result. They presented the results in a conference press. Probably that was one of the first conference press in science, right? They confirmed the factor of 2 of general relativity with respect to Newtonian case, although there were doubts for a long time. I think in the 60s it was National Geographic who they went through the whole thing, the notebooks and everything, and basically, apparently, according to what I have listened from them, the thing was okay. Anyway, so, and this is what makes Einstein famous. That conference press in London saying, now we have tested this thing of the field, that was make him world famous. Actually, he came to Barcelona, for instance, to many places, but in particular in Barcelona was 5 years later. It was came here, invited by in honors of great honors and everything, you know. But then after this thing, there was a hibernation. Yeah, the technology at the time was really not very good, so not many things to be tested. And yeah, there was a series of works, but actually it was, I think it was mainly by mathematicians. So and they were not very interested in the physics. They were interested in the, you know, differential geometry, the tensors, the curvature. So basically, yeah, that was yeah, and then the field stall, and then there were 2 predictions that were not tested from the original times. One is the gravitational redshift, and the other one was the system of gravitational waves, that too, as you know, much longer, right? But then, okay, we get to 1916, and then it starts a bit again the golden era. Okay, so there was this first conference, what we call GR0, General Relativity 0. It's the conference of the I think I don't know whether it was already founded here, the International Society of General Relativity and Gravitation. And Robert Dicke was at the conference and gave this. He said this. It's unfortunate to note that the situation with respect to the experimental section of general relativity theory is not much better than it was a few years after the theory was discovered. This is in strange contrast with the quantum theory, where we have thousands of experimental checks, and relativity almost is a purely mathematical formalism, blah, blah, blah. It would be great to challenge the experimental physicists to improve the situation, blah, blah. And then, indeed, this is what happened. So there was much better technology. There were also discoveries in astronomy, quasars, pulsars, cosmic background radiation, and as I said, technology, atomic clocks, lesson ranging, cryogenics. Okay, and then, you know, people start doing experiments in general relativity, right? So the first experiment is what is called the Pound-Redka experiment, which basically is testing the gravitational redshift. So it was done here in the Jefferson Laboratory in Harvard, and the US using the most powerful experiment to see that there was that you know, the reason why certain gravitational field decreases, there is a gravitational redshift when it doesn't. Well, from a region with a weaker gravitational field. So when you go to weaker gravitational field, there is a redshift in the gravitational, well, in the light that you send. And the other one was the Hossan-Taylor binary pulsar. Was a Nobel Prize in the 90s already. I mean, you know, they proved that there was this binary in a binary this pulsar in a binary system. The other one was a neutron star, and basically they checked that the orbit was shrinking because there is emission of gravitational waves that it takes energy, angular momentum, and therefore the orbit has to decrease. So yeah, the comparison of the decay of the orbital period with respect to the GR value is amazing. So yeah, so that and then there were other binary pulsars that also put really very stringent limits into the deviations from general relativity. So yeah, actually that was for many people, for the people that we were working in gravity, that was our only argument, right? And when we went to funding agencies, we want to do an experiment in gravitational waves. Yeah. Why? And then that was the only thing we could show, but and kept the field alive for many years. This is not linear regime, but it's still weak field. Right? This is something to take into account. And now in the 80s, this is where we wanted to enter into, try to see whether we can test strong gravitational fields, right? Yeah, well, this is maybe I'm going to skip. Basically, that you need some figures of merit to quantify the strength. I mean, you can do it with the Newtonian potential divided by c squared. This is adimensional, and then in the solar system gets you 10 to the minus 8. But with pulsars, if you are close to the pulsar, like the neutron star is 10 to the minus 1, but the one related, the gravitational potential related to the binary, the bounding of the binary is only 10 to the minus 6. That's why the Hudson-Taylor is weak field. Here we have some of the phenomena like the Shapiro effect or something like this that depends on the gravity at the surface of the neutron star, which is a strong field. But this is a stationary strong field, right? Not radiative strong field. And then of course, as I said, near the neutron stars and black hole, this is where we want to go, right? Yes, I can skip this. Then we can ask many questions, you know, about general relativity, cosmology, equivalence principle, Lorentz violation, blah, 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 blah. And then the contemporary perspective, first of all, let me give you what is the situation, right? So this is are the scales in which we test gravity, right? So below the millimeter, we know very little because gravity is very weak and it's very difficult to put two masses close by and see what happens, right? At the solar system scale, okay, it's very well tested, probably is the best one. Then there is a scale where we have no precise data, and then we have, you know, the large scales where, you know, it's also not very well tested. Things are coming. There are many theories that appear at each length scale, which produce modifications, and this is what people have been trying to do in the last times. And at each scale, you have different types of experiments. You know, now we have, as I said, we have the torsion balance, but now we have also cold atoms. There is less enranging. These are sometimes planetary missions that we can also test things by sending signal to these planetary missions. Okay, and then cosmology and gravitational waves is also related, right? But okay, the idea now is that gravity is different from the other forces. It's not even a force. It just tells you how the space-time is, and basically couples to all the other fields that you may imagine, right? And this has a lot of implications. So it's like the outcome of non-local gravitational experiments, you know, shouldn't depend on the local frame where they are perfect. They are good. And that they shouldn't feel that the experiments shouldn't feel the cosmological evolution and not have preferred directions. So there have been a lot of experiments in the last years to test the weak equivalence principle. Recently, we have here the microscope mission of ICE-CSIC, the French space agency, which went very now. Put it down here, and there are other experiments that can go even around here. Also, test of position invariance, many of them. Also, local test. This is like generalization of the matrix of Morley. Again, we have done many of those. We have tested that the fundamental constants doesn't evolve either significantly. You know, there are very strong constraints. The same for the variation of the gravitational constant. There are a number of constraints coming from different types of experiments. And okay, if you want to parameterize, you want to study deviation, you have to parameterize these deviations from. Actually, this is the metric that the Astronomical International Unit tells you that you have to use for the solar system. There is a resolution, I think, in the 1990s, I think it's a simple metric, but then in the 2000s, I think there is a bit more complicated one. Anyway, you take this metric and you start adding terms with parameters, and you measure these parameters. So many of these are here the parameters. In the other two are 1 and the others are 0. Yeah. So then people start doing experiments or observations in some cases, like perihelion, Norvet effect, spin precession. Well, many experiments, and then you start putting constraints on all these deviations. So this is an ongoing effort. Yeah, nothing indicates that we are deviating from general relativity. This is like for this parameter that have been a lot of experiments to different types, the diffraction light and the Shapiro time delay. Okay, many things are improving. You can also study modifications on Newtonian gravity. You see here, this is from very small scales, and then you start growing up to bigger scales, basically not beyond the solar system. This is what we can do. But again, and actually this we can test, like, extra dimension theories, many things can be tested with it. There was also the idea of electromagnetism, the idea that, like in electromagnetism, you know that you can create electric field by a charge, but if you have a current, I mean charge moving, this generates a different type of electromagnetic field, because this is a current of charge. You can generate a magnetic field. The same happens in general relativity, and then in particular you have, let me see, you have two effects. One that is the dragging, because the Earth is rotating, and the gravitational field of the rotating Earth is dragging the reference system, and in the reference system you have a spin. Then there is a geodetic effect that makes it move. So Gravity Probe B was one of the most expensive missions that NASA has done with a university, in this case Stanford. It didn't work very well for the geodetic precision, which already we know. I mean, we had a very strong limit, but for the frame, for the one, but for the technology it was not so good. There were problems, technological problems, despite I don't know how many decades they were doing to get this thing here. And then we have gravitational waves, where, I mean, we have, this is the typical gravitational wave of a binary system. There is a spiral phase where, it's a more Expositonian. You can check here, check whether gravitational waves propagate as general relativity tells you, or you have more polarizations. Here, when they are almost going to collide, then you need to do simulations in supercomputers. But here you can test. This is the most nonlinear regime where you can compare with other theories of gravity. If you manage to do simulations in the other theories of gravity, which is another thing. And then we have a last part where the black hole relaxes to a single black hole, that it emits this famous quasi-normal modes that only depend on the mass and the spin. This is what we call the Horner theorem. These are dumb sinusoidals, and then if we manage to measure some of these quasi-normal modes, we can check whether black holes are like general relativity tell us. And then I think with this I'm going to finish. I think I gave you a lot of information. I put you here the conclusions, where you can see the different levels in which we have been tested gravity, and in theoretical level. Now we have in the last years new avenues to connect with quantum physics. Okay, but this is for another talk one day. Okay, thank you very much for your attention.
Thank you, Carlos. So, do you have questions, Carlos?
So you said that one of the ingredients of general relativity for Einstein was the Marx principle. But is that really the case? It's really part of the theory, or is not?
Actually, the first thing I did in general relativity was I was working on this. What? No, no. In the end, it didn't play a role in the construction. And then we have the problem is that again, it's a matter of interpretation, because you have Schwarzschild. Schwarzschild is a vacuum solution, but you have gravitational field. So the gravitational field is not determined by anything in the infinity, because there is nothing in the infinity, right? So you will say that vacuum solutions doesn't satisfy Mach principle, right? But it's true that also somehow you take the whole black hole. This is not a real physical solution, because it's an eternal black hole that has been there for all the time, and this is not physical, right? So yeah, I mean, it's more interpretation than I don't think that anybody has said that it's violated or there is a big contradiction, but it was not built in the theory. Yeah.
It has not been proved. It says that nobody knows if the Mach principle is so correct.
Well, Newtonian level, I think is, well, I mean, in the end, is in reality, when you ask Newton why, when you have a bucket and you rotate it, why the surface of the water gets like this, and then Newton will tell you, oh, because it's rotating with respect to absolute space, right? And then Mach was saying, no, this is bullshit. There is no absolute space. It's because it's rotating with respect to the distant stars, right? So, well, yeah. So what? I mean, you cannot refuse this, right? I mean,
I have a question.
Yes.
So maybe you can tell us, like, in a few words, what do you think that the Einstein telescope will bring in this? What kind of avenues?
well, I think in the Einstein telescope and LISA, which I call the two of them because at different frequency bands, it's like they are going to make a leap in sensitivity. They are going to bring us to a new scenario if they happen at some point. I mean, the guys of Einstein telescope, they have not even decided where to put it, and they have the money. So okay. Anyway, but yeah, I think that we are going to get, for instance, all these things I said about the cosmic modes. Now with LIGO we are seeing one mode or two modes, and then people is killing themselves. No, you haven't seen anything. No, I have seen it. Oh, I know, but this is in reality it's a non-linear effect. But I think these things will be real science when Einstein telescope and LISA come, and then we will see whether I can give a talk at some point before retiring saying, no, yeah, there is general relativity is not anymore valid, no? But let's see.
Can you say a word on the
It's 13 hours.
new avenues?
Yeah, actually, yeah, people, people have this idea since long time ago, we have to quantize gravity. Why? No? And then I think now that people is getting, there are two directions, like classical gravity, quantum physics. And there is one direction from gravity to quantum, which we see is like we are realizing that general relativity knows about quantum. Right? Because, for instance, the entropy of a black hole, they're not doing any statistical mechanics calculation, and it gets exactly. You go to whatever favorite theory of quantum reality you want, string theory, whatever one of these things, they give you exactly the same value of general relativity. How is it possible if general relativity doesn't know about right? So then there is also this holographic principle. There are many things that on the other side. Now there is people saying that like things like entanglement states in quantum physics, that they could be linked to these solutions of general relativity, that's like the Einstein-Rosen bridge, and that this will be like elements. So it's a kind of a getting closer, but not the typical thing. Oh, I have to quantize this with a mathematical formalism. Right? So I think it's going to be different from whatever it happens. It's not going to be I quantize this. That's what I mean.
I have a very naive question. So you have shown us how we have been able to test, or people have been able to test very small levels, but with the entropy basically principle is okay and so on. Very tiny numbers, 10 to the minus 4.
Yeah.
What's the limit? I mean, where do we decide? Okay, this thing is working, or always being what is setting the limit when we decide, okay, we have been testing it? I mean,
Right.
it's stupid, I'm sorry.
No. I think it's I think it's a very valid question, because I mean sometimes probably that, well, I mean, all of us know that sometimes we can do very good experiments because there is somebody interested in the technology we are going to develop to do the experiment, right? So I think as long as you have a reason to convince somebody that what you are going to test is going to generate. I mean, now we have the optical clocks. I mean, we have to change the definition of the physical constants because they are getting so good that the definitions of time they were already less precise than the reference of time, right? But on the other hand, yeah, I mean, this is what happened a little bit like them, proposing experiments to prove that something is valid is not very cool these days, especially if you are going to spend hundreds of millions of euros. For instance, I have been involved with some people proposing to ESA, to the same mission, like testing the equivalence principle with cold atoms, right? I mean, we proposed this like 10 years ago. I think at that time it makes sense. And we were very close. Actually, it was when Plato was selected. I mean, we were in the last 4. But in the last proposals, SI is telling us, okay, yeah, but what is the science case? The science case is to tell me that you are now proving the equivalence principle to 1 part in 10 to the 18, right? So, yeah, maybe it's an overkill to use a emission. Actually, I told my colleagues, come on, we have to think about something else, right? I mean, now people is putting the other experiments that are a little bit less and profiting infrastructure like point. Some people is sending atomic clocks to the International Space Station. And that is actually now there is one, it's called ICE that have been deployed recently and probably will improve the microscope results. And there are some other ideas, which, you know, it goes down in the level and it keeps you, it keeps industry developing better and better atomic clocks. So, okay, this is it.
So do you think that a very tiny difference, as could be in mercury, perihelion, was considered back then as a
Right.
immensely tiny,
Right.
and it opened completely also?
Yeah.
Question.
No, but the thing is that
We are in this situation that
right.
we find a very tiny difference, it may completely open a new field, or it's going to be corrections, like
No, yeah, I mean, you have all these theories that quantum theories that, of course, I mean, as they are these days, the deviations are ridiculous. Even sometimes for the things we can, I mean, you mentioned as in telecom, maybe for a faster telescope, these theories are not producing anything measurable, right? So I don't want to give the wrong impression. I think that some sectors of the theory as equivalence principle are super well tested, and maybe we shouldn't worry too much because, okay, yeah, a couple of 3 more zeros in there. I mean, okay, but there are other regimes and also scales like that are not so well tested. So maybe we should focus on those things that we didn't reach because we didn't have all the ideas or the technology, and then try to see. I mean, as often probably people in cosmology are always going to help. But I mean, there are other things that probably are more interesting than not putting a few zeros more in the equivalence principle or whatever, or Lorentz violation, and that we know that is super small. But yeah, you talk to people in high energy physics, they go, no, we are interested in still Lorentz violation to a level in, you know, whatever, you know. Anyway, yeah.
Okay, so if there are no more questions, let's thank Carlos again.
Okay.
And as always, wait for the speaker before you start.
Don't worry about me.